I guess that Francesco made all possible comments about general situation, and my contribution will be a stabilizing one. So I will try to give some stabilizing effect. I will speak on foundations on this problem of generalized continua, and I just published some papers which are cited in the summary, and many we have the problem of reviews today. Many reviewers said there is nothing new because of the equations look like the usual equations, but the difference for me is in the nature of the approach, and foundation have to start from the very beginning. So at the beginning I will bore you with some recollection of what is the traditional approach to classical continua. Everybody of us knows about that, but it is important to state the point of departure. Then I will propose an alternative approach, which is not mine, has been worked out since at least 50 years by many people, but the current literature in science seems not to have got the right conclusions from this enormous mass of work. And then I will go to generalized continua, and I will make two examples because they are well known, consider continua and strain gradient plasticity, and they are different from each other, so we will be able to see the difference of the two. So let's start with the traditional approach. I see that the titles, we cannot see them, okay. The traditional approach, we start with selecting a set of external actions to declare which are the actions which act on the body. And in the classical theory we have distance actions, which means body forces, and contact actions, which means surface forces. With this we construct the classical Euler laws of motion, which are the adaptation to continuum mechanics of the first two laws of Newton. And I say motion, you don't see any acceleration here because the inertia forces in presence are here in the body forces. So there is no substantial difference for what I am saying to speak of equilibrium or motion. Then another thing which is not so much mentioned in the literature, but which is really fundamental, is the so-called cut principle of Euler and Cauchy, which says that what happens to the boundary of a body happens also in the interior. That means you can treat every part of the body as if it were the body itself. And this is not always realistic, but this is one of the bases of classical continuum mechanics. And then we have the Cauchy hypothesis that these contact actions, when you consider a part of the body, depend on the surface of that particular part only through the normal. This was a hypothesis of Cauchy, but it has been proved as a consequence of the laws of motion by Walter Noll in 1959. So I will refer to this fact as Noll's theorem instead of Cauchy assumption. After these premises, we go to theorems. The first theorem is the well-known tetrahedron theorem of Cauchy, which says that this dependence on the normal is linear. And then this allows us to write the equation of the motion on a local form. And to write the equation of virtual power, just take this equation, multiply by virtual velocity v, and make the integration, use the divergence theorem, and you get the virtual equation of virtual power. Here is the external power, here is the internal power. And the terms which appear in the internal power are the stress of Cauchy and the symmetric part of the deformation gradient, and these are the variables which are put into relation by constitutive equations. Then we add a set of boundary conditions, and we put the constitutive equation into the equation of virtual power, and we have the weak form of the equilibrium problem, and so on. This is an elastic case, but we can generalize this. So this is essentially the format that we follow in classical continuum mechanics. So let's see which is the alternative approach I was speaking before. We start from a definition which is pure mathematics, and this definition is fundamentally appeared in a paper by Gutin and Luis Carlos Martins in 1976. A Cauchy flux is the introduction of this entity, which is a vector-valued measure. Vector-valued measure means simply a function which with every surface element associates a vector which represents the action across this surface, which is additive on disjoint surfaces. This is a measure. And we define a measure to be skew-symmetric if we consider the surface with an orientation, and if we assume that if you change the orientation, the vector itself changes its sign. So let's consider this Cauchy flux restricted to surfaces which are boundaries of a body. Okay? In this case, we can imagine that this vector, this flux, is a function of the body itself, a function which I call f, capital F. So I consider this particular flux over surfaces of a body as a function of the body. This minus I is just convenience, has not. The first question we pose to ourselves is this Q is a measure that is additive on disjoint surfaces. The question is whether or not F is additive on disjoint bodies. So if it is itself a measure. And the answer is in this theorem. F is a volume measure if and only if Q is skew-symmetric. So you see that in this case, to assume skew-symmetry of the actions, which means the third Newton's law of motion, becomes fundamental, while in classical continuum mechanics it was simply a consequence of the balance laws. And here in this approach recovers its fundamental role. There are other theorems, because now that we know that capital F is a measure, we have to see whether or not these measures, capital Q and capital F, have densities. So S is capital Q is expected to have a surface density on surface, and capital F is expected to have a volume density on volumes. And the answer is the following. Q is, I just give a sufficient condition. There are also necessary and sufficient conditions, but I have no time for that. If Q is dominated by the area of the surface to this constant K, mathematically this is a Lipschitz continuity assumption, then Q has a surface density, and for the volume is the same thing. If the same Q restricted to the boundaries of the part of the body is dominated by the volume of the body, we have a volume density. If we have the two densities, this equation can be written in this way. okay, with densities small f and small s. This equation that we obtained looks very like to the equation of the balance of linear momentum, but it is not the balance of linear momentum because we have no body forces here. This is just an internal property of the contact actions. This is a regularity property of the contact actions, which says that a contact action defined over the boundary of a body can be expressed by a distance action. So there is no balance here. This is why I propose to call these equations pseudo-balance. They look like balance, but they are the balance of nothing. This is an internal property of the system of the contact actions. So, but this equation has everything which is necessary to prove the null theorem and the Cauchy theorem, which start exactly from an equation of this type. Okay? Only the physical meaning changes. Before, the tetrahedron theorem was a balance between two different actions. So here, it is an internal balance for the contact action. So this, what you saw before, this the existence of a stress tensor T is an internal property of the system of contact actions. And if you think a little bit, this is perfectly logical. I mean, the contact actions are regular, then I can define a Cauchy stress with no need of volume forces, of distance forces. And we deduce the local pseudo-balance equations. Here I have the volume density of the contact force this time. So it looks like the classical one, but it is not. And then the question is, where do we introduce the balance actions? Because these are laws of mechanics. They must enter sometimes in the play. Okay. There is another fundamental result by Walter Noll, is that the balance equations, the Euler equations of motion, are a consequence of the indifference of power. That means if you define the power, as we did before, and we suppose that this power doesn't change if you take a rigid motion of everything, then that means this is the external power. If you take virtual displacements, which are infinitesimal rigid displacements, then the power has to be zero. This is a difference of power. In this case, you get the classical Euler equation of motion. So if you compare these equations with the previous pseudo-balance equations, you simply get that B is equal to small f. That means that in the classical continuum, the distance action is equal to the external action is equal to the density of the volume density of the contact actions. Okay? This is the result of this comes from the pseudo-balance equations plus the indifference of power. So this I just said. So at this point we can simply take the external power, which is defined in this way with with distance action and contact actions, to transform it this way, and we get the internal power. That means that the internal power is not something independent of the external power. You deduce it simply by taking B. This divergence of T is the small f. You put them together, and you use the divergence theorem, and you automatically get the internal power. It is deduced and not separately assumed. Then, this structure of the internal power tells you that T is the internal force, and the symmetric part of the gradient of V is the generalized deformation. You put them together through constitutive equations, and you can write the equilibrium problems. So you see that in the classical continuum mechanics, there is no big difference between the two approaches, and this can be considered as a matter of taste. Where the difference becomes important is when you go to generalized continua. In the case of generalized continua, you see that there is a difference between the two approaches. So let's speak at first about generalized continua in general. So to make a generalized continuum means to add to the initial kinematic variable u some extra variable which I call order parameter, as is a set of variables. Alpha is just a counting index, and these variables may be scalars, vector tensors, that depends on the nature of the continuum. And I call V and U sub alpha the corresponding virtual variations. Then, with each one of these kinematic quantities, I divide the dual quantities, which are forces. So I have the forces of classical continuum mechanics plus what I am calling here body microforce and surface microtractions that may be of a very different nature. And with them, I can define the external power. I just add these green terms to the preceding terms, which were the terms of the classical continuum. Okay. Where this S and this sigma come from the Cauchy theorem of the tetrahedron, which is applied independently to both quantities, classical and generalized quantity. Then we use the pseudo-balance equations. That means, I suppose, that even for the new variables, the contact actions have the regularity supposed for the classical ones. So I can define, besides the small f, which was the volume density of the classical variables, some volume density phi sub alpha, which are volume densities of the new quantities. And I have the pseudo-balance equations. One is the classical one, and one is the equation of the new variables. And this is an important point. As you know, there is interest in these generalized continua since the 1960s. Okay? Because of the work of the Cauchy at the beginning of the last century was forgotten for 50 years. And then there was a big revival at the beginning of the 60s with the papers of Mindlin, of Tupin, and others. And by the time I was almost a child, but I read these papers, which were almost unreadable, and I wondered which type of equations. They got equations like this, which were called microforce balance equations, something like that. So what I was not able to understand, which type of equations are these? Because if they are equations like this one, they should be equations of balance, general laws of mechanics. And it seemed very strange to me that every special continuum generalized continuum has to introduce its own general law of mechanics. Others say that they are constitutive assumptions. So the problem is why the classical balance laws are general laws of mechanics, and the other ones are constitutive assumptions. And this was a point which was very difficult for me to understand, and now I got an answer, at least for myself. The answer is that they are all pseudo-balance equations, so they are all consequences of regularity properties of the system of contact actions. Okay? The balance equations are something extra. So you see here I have small f and not small b. We are just speaking of regularity of the contact actions. So we use an old Cauchy theorem. We have the classical equations here, plus we have the new equations, which means there exists a tensor, sigma sub alpha, for every new variable, and this may be vector, a second-order tensor, or third-order tensor, fourth-order tensor, depending on the nature of sigma, and we have the local form of the new pseudo-balance equations. So at this point, we simply write the external power as the sum of the classical plus the new terms. We use the machinery I said before, and we automatically get the internal power. That means this procedure tells me which are the generalized forces, in this case T and sigma sub alpha, and which are the generalized deformations, which are not only T and sigma sub alpha, but also B minus F, and beta alpha minus phi alpha. A priori, we have 4 types of generalized forces, and each one has its own generalized deformation. And at this point, I use the indifference of power, but I cannot be general on this point, because this is we saw that to define a general continuum, we have to do 2 things till now. The first one is to declare which are the variables, and second, to assume that the internal forces have some regularity properties. Now we have to do a third thing, to declare which kind of indifference should these variables enjoy. Because this is a physical fact. I am representing a continuum. I must have clear in my mind which are the indifference properties of the variables I am introducing. Okay? So this depends upon the specific continuum, and this is why I don't stop here, but I have to do examples to show how this works. Each set of these 3 operations define a class of continua. I mean, a continuum is now defined by declaration variables, regularity assumption, and indifference requirements. You see that usually after the work of Germain in 1973, it was very popular to start with the equation of virtual power, in which you had to figure out 2 different powers, internal and external, and then work on it. The question was how to define the external power, the internal power. Okay, they said that this is an independent assumption, but this is not true, because you cannot define anything as internal power, because you have to be careful that at least you recover the classical balance laws. So this cannot be a principle. This is derived from something. Okay? So my view is that the expression of the internal powers is simply deduced from the external power via the pseudo-balance equations. And, but we have to be careful later about supposing the right indifference properties. So a class of continua is defined by these 3 requirements I just said. And we have sufficiently freedom within each class to define a large variety of materials just by making specific constitutive assumptions between variables, between the variables which enter the internal power. Okay, so let's see how this works for the 2 examples I said before. Let's start from the Coursera continua, which everybody is familiar to most of the audience. In this case, simply the variables are triples of orthonormal vectors. So this means that they are not they are triples, but the variables are not 3 vectors because they are orthonormal, so they are related to each other in some way. And simply, they are related by a rotation velocity omega, which is defined in this way for each alpha. And so the powers of these actions can be reduced just by taking the mixed scalar cross product and so on, can be reduced to this form in which we have a single couple vector and a single moment vector. So we have a simpler form of external power in which the sums here, these sums, are replaced by a single product, which is a product between vectors. So I make the regularity assumptions, and I get a pseudo-balance equation. So this is a classical one, and this is the new one. This is just a special case of what I showed before in general. Simply I changed the name of the symbols. I have small phi and small m instead of the sums I had put before. Then I use the Knoll and Cauchy theorem. Here I have a pseudo-balance equation of the same type I saw before, but just a single vectorial equation. And I define the external power exactly the way I defined before, but with the new names of the symbol. You see, once we have clear what we have to do, this is like a machine. We start a model and we turn the machine, and the machine gives us appropriate equations. Now we have to come to the indifference requirements. And the indifference requirement is the following. Since these d alpha are material vectors, which represent some orientation inside the body, the power should be indifferent when I give simultaneous rigid deformations of the body and the vectors together. So we have power with a rigid translation and no variation of the directors equal to 0, power with a rigid rotation of the body, a rigid rotation the equal rigid rotation of the directors equal to 0. These are the two equations. So since this was the expression of the internal power, when I put V equal to a constant and omega equal to 0, I get the result of the classical continuum mechanics. And when I put this condition, we have to do some computations that I will not do here, but in this case, the phi, the volume density of the new variable, is equal to twice the tensor, the vector associated with the skew symmetric part of the tensor plus this C. Okay, so this is the way in which the equation, the indifference determines the variable phi. And then we can get a reduced form of the internal power, because this term disappears, and in this term we have a relationship between phi and 2t plus c, which leads to this equation, in which this script phi is just the relative rotation between the body and the director at every point. Okay? There are computations which I am skipping. Once we have this, we conclude that these are the internal actions of the Coursera continuum, and these are the corresponding deformations. Okay. So there is a constrained theory of Coursera continuum. I am happy we cannot read the titles here. Okay, internal constraint in which you simply put phi equal to 0. You suppose that locally the rotation of the body and the rotation of the continuum is of the directors is the same. In this case, you simply eliminate the first term in the power, and the second, and where you have omega, you have 1/2 of the curl of V. Okay? So this is just computation. It's very simple. So in this case, you have these internal actions, 1 and 2, and these generalized deformations. There are other And in this case, you see the variable omega disappeared from the expression because it is constrained. It disappeared on the expression of the power, which is just a function of phi over v. But so it looks like a continuum, but there is a microstructure. But the microstructure is latent in the sense that you don't see it explicitly. It is hidden because you introduced the microstructure, then you introduce the constraint, which makes this additional variable to disappear. But it is still there, but it is hidden. And we have other special theories of Coursera media. That means if we introduce these constraints on V and omega, related to the existence of a privileged plane, E1, E2, you get the Reissner theory of plates, just by turning the machine, I mean, without any extra effort. And if we constrain this omega to be equal to the rotation produced by V, we have the Kirchhoff-Love theory, and the same happens for the beams. For the beams, you could just change this internal constraint, you get the Timoshenko theory, you constrain this omega, and you have the Euler-Bernoulli theory. So everything comes in a very simple way from a general scheme. Okay, let's go to the last example, which is the strain gradient plasticity. In this case, we start with the composition of the deformation vector, and we take the plastic part as an order parameter, which is a tensor this time. We have a tensorial order parameter. So this is the composition of the virtual variation of f, which is a sum decomposition into the velocities of the plastic or the elastic part, and this is our virtual velocity. So there are special theories, okay, scalar theory in which the tensor is fixed and only changes the scalar multiplier, or crystal plasticity in which this is a sum of dyads, and in the dyads we have vectors which reproduce slip planes and slip directions. So we have this order parameter. These are the corresponding dual quantities, volume and surface, and this is the volume quantity of the surface density. And we have the pseudo-balance equation of this type, which are exactly the same as before. Only the names of the symbols of the quantities have been changed graphically. We have Knoll and Cauchy theorem. This time S is a second order tensor, this T is a third order tensor, but the equations are the same. This is the expression of the internal power, which is exactly the same as before with the changes I just said. And now we have to introduce indifference requirements. In this case, the state variable refers to a deformation undergone by the intermediate configuration in the plastic decomposition. And this intermediate configuration, just as like the reference configuration, is not affected by a change of observer. So in this case, we don't have any condition on the new variables, and the conditions are exactly the same as in classical continuum mechanics. So we have the same conclusions as in classical continuum mechanics. B equal to F and T should be a symmetric tensor. So if we write the power, here we can put the symmetric part of V because T is symmetric, and then we have this part here. So in this case, the capital phi did not disappear from the equation of power. That means that in this model, the indifference requirement do not determine phi. So you are free to make constitutive assumption on capital phi. Okay? you have a lot of theory, and indeed, for instance, I read the papers by Morton Gertin, who wrote several papers on crystal plasticity in the Journal of Mechanics of Physical Solids, making different models, okay, in which there are different constitutive assumptions on this phi. Of course, he presented saying, I figure out a certain form of internal power, and then I compare. And since Morton Gertin is not stupid, he was always right. I mean, he chose the right model. But what was disturbing to me is to invent an expression of internal power which can be deduced from the principles. Okay? So, for example, I am going to finish. For example, okay, we have here the internal power. And here I introduced the composition of the deformation gradient into elastic and plastic part. And so the plastic part is here inside, has been transferred to the second term. And in one of his papers, what does Gertin? This internal force, he calls it T sub P. This is his internal forces he chooses, and he makes constitutive assumptions on this force, simply. Of course, his deduction is completely different, but this is what he is doing. So he obtains what he calls micro-force balance, which is our pseudo-balance equation, and an expression on the internal power. This is exactly his expression. In a second paper, which was done for viscoplasticity, so he needed that the intermediate configuration be isotropic in the relaxed state. In this case, he needed the isotropy of the intermediate configuration, and this can be obtained by this extra assumption of the power, that the power does not change if I take in place of LP, I take a constant vector. This is not. This does not come from indifference. He is very clear on this point. This is just a constitutive assumption, which looks like an indifference assumption, but it is not. In this case, TP, this vector, becomes symmetric. And this way we have that phi, our phi, which was not determined by the equation of power, splits into a symmetric, skew-symmetric part. The skew-symmetric part is just a reaction, is equal to the skew-symmetric part of the given body force, and the other one is determined as a function of this TP that he introduced. Then we have the micro-force balance, here it is. And this induces, because all these quantities are symmetric, we have that this T has to be symmetric with respect to the first two indices, and that means that this gradient of LP can be substituted by the gradient of the symmetric part of LP, and the same here. So we have a power which, instead of being function of the whole virtual variation of the plastic part, is just a function of the symmetric part. There are an infinite number of other possible theories. I just made a list, but I am sure that you can add an enormous quantity of models to this list. And those are those whom I checked, and they fit perfectly in this scheme, so I don't have any doubt for the moment that this can work for every other scheme. Okay, I finished here. Thank you.
I know that this is a very controversial subject, and actually I asked Piero to start, because this was a way for immediately
for starting the discussion.
I asked Gerard, please. I asked Gerard, please, to start. Yeah, to start discussing later, because we are already late.
No, that's a good one.
Okay, go ahead.
No, it's fine. I just have one objection.
Yeah.
You must be careful about the vocabulary.
About, sorry?
Vocabulary. Don't use the expression order parameter.
Okay.
Besides many implicits.
Okay. No, I just took it from the papers, but if you suggest a better term, I have no. Which is your proposal?
It might be the case in some cases.
Yeah.
Another parameter.
But what shall you use instead?
Well, I don't know, internal degrees of freedom.
But this is not a degree of freedom, this is a physical quantity.
Okay. Do you have the attention of the distinction?
No, I will take a... I will consider this objection because I'm not even...
Famous Italian scientist.
Who? Lagrange. Yeah, but I am reluctant to call it generalized variables because the adjective generalized. But I am open to any suggestion. If you have some proposal, I would be glad. Because I don't like as well order parameter. But it was the closest term in the literature.
And order parameters. It makes sense.
No, okay. You are completely right.
Attacking, but we will do it during.
No, but this is not an attack. This is a suggestion. This is a suggestion, and I appreciate that.
So, I just want to add the comment on a thing related to this one. First of all, of course, I appreciate a lot the clear presentation here. You concentrated, focus the attention on the frame difference rotations.
Yes.
But there could be other internal symmetry in the system. For instance, you may have, if you go to electromagnetism, you have this gauge invariant, for instance. So that this could be included in your way of presenting this. I mean, this could be a bridge going towards these things in elementary particle physics like
Yeah, I agree with you. I never considered examples out of classical mechanics, as you see. And about the example you are mentioning, it would be important to state whether these are structural properties of the continuum, which define a class of continuum, or if they are constitutive assumptions. Because there is a difference between the two. The first ones you will get from general equations, the other ones you get from specific material. Now, in your example, I don't know the answer, but the point to clarify should be this one.
Because the impression is that really they are related to they are not constitutive in the sense that you have this phase arbitrarily in the wave function, so that you can locally change the.
Yeah, but even here you see you can meet arbitrary things like the definition of capital phi without already specified class of continua. So I should simply study, and I don't have an answer for the moment.
We have two more questions, but more. I
have a question concerning the distinction of external and internal power. If you like, I wonder if you agree to the following statement. If we write down the general expression for the power, then there's absolutely no way of distinction between internal and external ones. The form is the same. Only if we specify the dependence of the force terms, of the dynamic terms, on long range, short range, etc., then we are able to do this.
No, I don't agree with you, because in my view at least, then I may be wrong, of course, the external power defines which is the interaction on the body from the exterior. The internal power describes what happens inside the body. Now, many people, like Di Carlo, for instance, took the internal power as primitive. But this is just an operation of brain, because you already know the theory, and then you decided that it is more comfortable to start from the internal power. But what is always done, you study the phenomena, you study the interaction with the exterior, and this is your starting point. Then you arrive at a level of generalization. For instance, another viewpoint that I didn't mention is the energy approach. You write an energy, then you minimize the energy, you get the equation. This is even more an intellectual operation, because you start from known phenomena. You arrive at writing an energy and say, okay, from the energy I can deduce anything else. But you don't know a priori how the energy looks like. You have to construct it. Okay? So these are intellectual operations that are possible once you have a sound theory. In general, in mechanics, the variational principle were those were inventing a functional for which the known equation of the virtual power is the Euler equation. So it is a sort of reverse procedure.
Sorry, there are many. We go ahead because this is the essence of everything. In this moment, you are playing the role of a famous Italian mathematical physicist, Piero, and he sounds like Poisson. I am on the side of Piero, but Roger is before.
I just had a comment. In the beginning of your talk, it seemed like you were giving a new definition, sort of like a divergence theory, basically, the divergence theory, classical divergence.
Why?
Because you wanted an area integral to be evaluated.
Yeah.
In some way.
Yeah.
And in some way, that happens through a divergence theory, but you postulate that.
Yeah.
It's not but I know that you kind of proved it. Or perhaps also no Lagrangians were in your mind. I don't know. I think they're both related.
Yeah, maybe. Yeah. But I use the classical divergence theorem, not more than that. But there is a huge literature about Miroslav Shiravi, for instance, made a lot of, and then the people in Brescia, like the Giovanni and the others, about what happens if you have singular measures. I could just consider the regular measures. Then they defined fields in which the divergence is a measure and so on. There is a large literature on this subject, but I didn't wish to enter inside.
So we have 3 minutes, 1 minute each.
A comment about the way you change the name of Cauchy assumption into null theory.
Yeah.
I think that there is a danger by doing this. You are changing the status of this assumption in something which cannot be questioned anymore. But indeed, in this theorem, there are also assumptions. So I should prefer you to call it null assumption instead of null theory.
No, what he said, what he proved, if you have an equation with a surface and a boundary term, then you have the dependence on the normal. That is all. Of course, you can make some more general assumption. In these general assumptions, the null theorem doesn't work. But I was speaking purportedly of the classical continuum, and I extended the structure of the classical continuum. And within this range, it is a theorem.
Yes, it's a theorem, but as the basic of this theorem are an assumption, which indeed it has...
But this is another point. A theorem starts from an analytical assumption, and within that analytical assumption is true. Of course, if you change the assumption, you can get something else.
But doing this, you are giving a physical assumption by something which looks like a mathematical assumption. But indeed, they are the same assumption.
No. I just saying from this integral I can deduce that, and this is just a theorem.
Okay,
you can question the point of departure. Okay, you are free of doing that.
Go ahead.
I'm sorry for maybe a stupid last question. I missed how we get the symmetry of the flux from in the pseudo balance equations when it's the case, because sometimes we have the symmetry and sometimes no.
Yes.
So how?
This depends on which indifference requirement you get. For instance, in the classical continuum, you just have a single term in the power, and the indifference requirement gives you the symmetry of the stress. When you have several terms which interplay between them. It is not, you have a restriction on the symmetric part. Okay. So this comes very simply from the equations. Yeah.
Okay. Thanks a lot. Another question? Go ahead.
Parameters seem to be, you need to mention what space they belong to. So if, for example, you talk about damage, it's not something that you have in the previous structure for.
You have, excuse me.
If you talk about damage,
yeah.
So your damage parameter is not a point in a Euclidean space.
Yeah, but because you take damage variable between 0 and 1, you mean. Yeah, but you can take just a to the alpha to the minus 1 and goes from 0 to infinity. Yeah. Yeah.
So how do you end up values of this parameter at different points?
Yeah, but this becomes a constrained problem with its own complication, but this doesn't affect the theory. I mean, no, I say we start from very simple assumptions, okay? And then you say there are situations in which these assumptions do not work. Okay, we can take of them separately. I am not claiming to make a completely general theory which encompasses everything. I am just saying what happens in a simple case. Okay?
Okay, thanks a lot.
Thank you.